Hi, I'm Arya Hakimian, application scientist at C-Therm. In thermal management, one topic that always sparks interest is the use of fillers to improve a polymer's thermal conductivity. Today I wanted to walk through what fillers can do, and just as importantly, what they can't. Because while fillers offer real benefits, it's not alchemy that magically turns a low-K polymer into a material rivaling the thermal conductivity of a pure metal. Base polymers typically have a relatively low thermal conductivity, often between 0.1 and 0.3 watts per meter Kelvin. Now that's great for insulative applications, but not ideal when you're designing a material to rapidly dissipate heat, like in a thermal interface material. That's where fillers come in. They create pathways for heat to move through an otherwise insulating matrix. When you introduce fillers like alumina, boron nitride, or graphite, you're essentially adding thermally conductive particles that help redirect heat. As concentration increases, these particles start linking up to form networks, and that's what really drives improvement. It's not magic, it's connectivity. Now, even with heavy filler loading, polymer composites still won't reach the thermal conductivity of a solid copper or aluminum, and that leads to another critical consideration. How much filler to add? You need enough to form continuous heat transfer pathways, but pushing the loading too far can introduce new challenges. High loading levels increase the material viscosity, this affects flow during molding, and can even make the part brittle or heavy. So the challenge is always finding the balance, enough filler to achieve thermal performance while keeping processability and mechanical properties in check. At C-Therm, we help researchers quantify the actual impact of fillers on thermal performance, and we start with the MTPS. Using the MTPS sensor on the Trident platform, we can perform thermal mapping across different regions of a part or a coupon. And that's powerful because fillers don't always disperse evenly. You may have filler-rich zones where percolation networks form, and filler-lean areas where thermal conductivity drops off. MTPS makes it easy to detect those variations quickly without complex sample preparation. Thermal mapping helps you answer questions like, are my fillers dispersing uniformly? Does one region of my part conduct heat better than another? Is my process introducing anisotropy or filler settling? Did we achieve percolation everywhere or only in pockets? By measuring multiple locations with the MTPS, you can get a clear picture of real composite behavior, not just a single average value. And that's critical when you're validating formulations or troubleshooting manufacturing issues. MTPS thermal mapping shows you where the heat is moving through your composite. And when you need a bulk average thermal property measurement for material comparison or validation, the Trident platform also supports other techniques like the more traditional TPS. Together, these methods help ensure fillers are not only improving your thermal conductivity in theory, but delivering consistent, measurable performance across your parts. If you'd like to learn more about MTPS thermal mapping or how Trident can support your material development, reach out to our team or visit tridentthermalconductivity.com. Thanks for watching.